Thanks, Alina, and thank you for allowing me the opportunity to come here and talk about my favorite subject. I am Doug Ming. I'm the Chief Scientist for the Astromaterials Exploration and Research, Astromaterials Research and Exploration Science Division here at the Johnson Space Center. And yes, I am a scientist. I have a doctorate degree in mineralogy. And I have been working here at Johnson Space Center for just about 30 years. When I first came here, I got heavily involved in the Advanced Life Support Program. And so for about 15 years, I worked really hard on that particular effort of how we could develop life support systems for long duration missions on the Moon and on Mars. Then about 15 years ago, I had the really unique opportunity to get more into back into the science that I was trained in. I had the opportunity to get involved in a Mars landing mission. Since that time, I've been very fortunate to be actively involved in 5 landed missions to the surface of Mars on the science and the operation teams. So, when people ask me what I do, I tell them, I say, I go to work on Mars every day. Now, I don't put my boots on the surface, but through the eyes of these robotic missions, I am able to do research almost real time on the surface. So it's great that I just get up and say, I'm going to work on Mars today. Now, I am involved in 2 missions right now. I'm involved in the Mars Exploration Rover Opportunity, and I'm also on the science and operation teams for the Mars Science Laboratory Curiosity. I have a job that I do for the Curiosity mission. I am what they call the Science Operation Working Group Chair. And what that is I am the one that leads the science team in defining what the rover is going to do for that particular day on Mars. Are we going to drive over there? Are we going to look at that rock? Are we going to drill this rock? What are we going to do? So I've been heavily involved in leading those tactical operations, and it's been really an honor to be in that position. Now, we all know here in Texas, everything is bigger in Texas. We've all heard that. How many times? Well, folks, Mars has really big features. Valley Marineris stretches all the way from the eastern to the western coast of the United States if it was here on Earth. And Olympus Mons is the highest volcano in the solar system. It's 3 times higher than the highest volcano on Earth, which is Mauna Loa out in Hawaii. And that's from the base down in the ocean all the way to its top. Now, we landed in Gale Crater with Curiosity. And things are also big for Curiosity in Gale Crater. It's a 155-kilometer wide diameter crater that has this mound in the middle. Notice I said mound, but to us here on Earth, that is a mountain. It's over 16,000 feet high from the floor of the crater itself. And you can see Mount Rainier is only about 14,400 feet. And so if you're standing in Seattle, Tacoma, looking off at Mount Rainier, that is an incredible view. Well, you can well imagine the view that it is for our rover, Curiosity on Mars right now. So the prime goals of the mission are to characterize and assess the past habitability at the landing site, both present and past. Could life have evolved and could it have persisted there? We're doing that by looking at the biological potential. What are the elements for life? Are they there that are necessary? Characterizing the geology and geochemistry, looking for water. Water is important for life, right? And then also looking at the record in the rocks themselves, the mineralogy, to look at what past climates on Mars might have looked like. We also have on the payload and the capability to do radiation assessment. We launched November 26, 2011. We landed August 6, 2012. And this is an incredible image caught by our high-rise camera on the Mars Reconnaissance Orbiter as the parachute and spacecraft were going into entry, descent, and landing. Now, EDL, this was 6 to 7 minutes of terror, they called it. And there was a lot of things that happened. Parachutes deploying, slowing down the spacecraft, breaking away from that parachute, and then descending to the surface with a controlled descent lander in the form of a sky crane. And on a tether, we rolled out the rover. When it hit the ground, the wheels were deployed. We were ready to roll. The sky crane was released and flew away. This image is a high-rise image. On the left side are the burn marks from that descent lander, you can see. And then we made tracks over to the east about 1 kilometer-mile, and you can see the rover tracks of Curiosity here, to an area called Yellowknife Bay. This is a low, and in these lows is where you would expect what? Water to accumulate. So our theory was this was an area where water might have actually ponded. On our way down there, we stopped at this wind-blown deposit called Rock Nest. And here you can see Rock Nest in front of the rover. We used the scoop to scoop up some of this material. This image was taken with our geologic hand lens, the Molly, that was out on the end of the arm. And back off in the distance, you see that monstrous looming Mount Sharp. Now, we took some of this material and we delivered it to our instruments. We also looked at the physical, chemical, mineralogical properties of this material. And you can imagine how important this is, not only for science, but to understand these materials on how they will interact with our humans and machines when they're on Mars. How will they affect our spacecraft? Suits, airlocks, and the humans themselves. All important questions that are being answered by the data sets being returned by Curiosity. Now, we delivered some of this material to one of our instruments on board the spacecraft. This instrument is a sample analysis of Mars, or the SAM instrument, and what this does, it heats the sample up and it sniffs the gases that are driven off with a gas analyzer. What we found? Water. About 2–8% of the material here was water. Could this be used for propulsion systems? Could it be used for life support systems? This is something we need to consider. We also saw oxygen, hydrochloric acid, along with some chlorinated hydrocarbons being released, and we've attributed this to a compound called a perchlorate salt. Is this stuff useful or is it dangerous? Something we need to understand. So we headed down into this low, this depression, our hypothesis of this lake deposit of Yellowknife Bay. And we came to this area that we call the John Klein area. And if you look at this, and it's been a really dry year here in Houston, we got lots of clay. All of us know what clay is here in the Houston area. And this material is wet, it's ponded, it dries out, it cracks. These are mud cracks. Now, these aren't exactly like the ones here in the Houston area, but these materials have a lot of the same properties. They're a little more resistant, there's a little bit more fractures in this, but there are larger fractures that we think could be to desiccation of potentially clay-type materials. We drilled a hole. We have a drill on the end of our arm. We were able to drill this material out and put it in one of our instruments on the rover, and in this case, we put it in the chemistry and mineralogy, the ChemMin instrument. And this instrument detects the mineralogy. Now, there are two images on this particular slide. On the left is this image of this sand deposit, this wind-blown deposit at Rock Nest that I just talked about, and on the right is the one from this kind of, we call it a mudstone, this really fine-grained material that we drilled out of this sediment. And near the bottom of this diagram on the right, there's this really bright region. And this is due to the diffraction of the X-rays, it's what's used in this instrument, to diffract off of the mineral, and in this case, it's a clay mineral called phyllosilicate. So we discovered that, yes, this stuff is like stuff around Houston. These are clay minerals, and we had about 28% of these materials in our sample. So our conclusion here in this brief jaunt over to Yellowknife Bay was that this was an intermittent river system with probably shallow lake deposits. Now, one thing also we found, we got the water, we have an environment that could have been supportive of biological systems. What about the key ingredients? We did discover carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, all key for living systems. So we did find what we call a habitable environment. Now, we left this little jaunt over to Yellowknife Bay, and we traveled 9 kilometers down to a place called the Pahrump Hills. Now, along the way, of course, we did a lot of science. And one of those, I love this picture, by the way. And I was actually leading tactical operations this day, and I said, since I got the final word, I was able to get this in. I said, I would really like to drive over this particular this deposit of wind-blown materials, stop the rover, take our eyes, turn around, take a shot of this, and this was a shot that we acquired. Now, this is great for, you know, it's a beautiful picture, number one. Number two, it provides us with some science input, but it really helps with us looking for humans. How will if we have a rover or wheels interact with these kinds of materials? How far do we sink? These are really key things that we are looking at that will feed forward to human missions. We also noticed that all of these sedimentary deposits, these layered deposits of sediment, were tilting towards Mount Sharp. What that told us is that these were probably transported by water systems, lakes, maybe falling off into a delta, from a river system, and they were all tilting and depositing towards the Mount Sharp, suggesting that this at one time had quite a bit of water here. We had a lot of water inside this crater, probably around 3+ billion years ago. We also discovered, not all the time, but once in a while with our sniffer, the atmospheric sniffer on the rover, that we discovered methane. And we didn't see it all the time, just once in a while we would get a signal of methane. Now we didn't get a lot, just a few parts per billion, but this is pretty significant. We're seeing methane. What does that mean? Could mean a lot of things, but these periodic discoveries of methane suggest that there's some kind of a local hotspot. Now, it could be that dust is raining down organic material from out there in the cosmos. UV light is interacting with it and degrading it to form methane. More likely, there's a geologic source underneath us that is spewing out methane into the atmosphere. However, we cannot rule out the possibility, if we were on Earth, we would probably attribute that methane to what? To living systems. That is one of the byproducts, methane. So it could be something dealing with life, but more likely, it's a geologic explanation. Now, our friends at headquarters, HEOMD, as we all know, was a very important contributor to this payload. They provided an instrument called the Radiation Assessment Detector, RAD, to look at the radiation environment, not only on the surface, but during transit. And what we found with this instrument is that if you were an astronaut going to Mars, you're on the surface for 5 days, you would basically get in transit and on the surface about 1,000 millisievert of radiation. Now, station for 6 months, 75 millisiemens. Here in Houston for 1 year, 2 to 3 millisiemens. So, radiation, we know it's going to be a problem. We're definitely going to have to address this with humans. Now, we just finished about a 6-month campaign at the base of Mount Sharp. We're here at what we call the foothills of Mount Sharp. We went up to this outcrop and we really did a detailed characterization here of the physical properties, the mineralogical and chemical properties, because this is probably the base of Mount Sharp. This is as low as we're going to get in the stratigraphic section, because here we go up, they're going to be deposited after this material. Now, this is a great image from high rise. This is this Pahrump Hills that I just showed in the previous slide. And what you will notice here is that the rover is just leaving Pahrump Hills and we're starting up this drive called Artist Valley. And today on Mars, it is Sol 971. We've had 971 days, Mars days of operation. We have gone over 10 kilometers of roving, and we right now are sitting at a place called Logan's Pass. That's where the rover is as we speak. So, how is Curiosity helping us to look forward to human missions? What is it providing us? Resources. What are the resources, information that we're gathering? Well, we know there's water. How can that water be used? Can we extract it? Can we then split it and use it for propulsion systems? Can we use it in life support systems? What about these perchlorate salts? Can they be used as a fuel as well, both in the rockets, propulsion systems, as well as in fuel cells? CO2 from the atmosphere. We know we got an atmosphere that contains CO2. Can that be extracted? Can that be utilized to potentially make oxygen for propulsion systems? Methane. Can we find a hot spot for methane? You know, methane's kind of a hot topic for propulsion systems around here at JSC. Is it a possibility we could use methane? And then the hazards. We got to address the hazards as well. Dust. That's always on everybody's mind. What is going to happen when humans get dust in their lungs? And then the radiation. We got a pretty good idea about the radiation from this mission. And then this compound called perchlorates. Is it going to be toxic? Something we will have to address. So our goal from here on is to continue exploring the lower reaches of Mount Sharp. And let me tell you what, from the view right now of the rover, it is absolutely incredible. We've got these layers, these sedimentary layers that contain iron oxides, they contain clay minerals, they contain sulfates, just a whole entourage of stuff. And the mission's really just starting now, because the stuff we're getting into is just absolutely stunning from orbit. I can't wait to get there in real life. So, on to the slopes of Mount Sharp. And as we do this, Curiosity is trailblazing, in my view, the path for humans to Mars. Thank you.